Alright, we've heard enough. Now let's see some action. I'm gonna show you a simulation of an attack against Kubernetes where the attacker will start attacking a container in a pod and move their way to compromise the host node and cluster. Let's first have a look at our architecture. We have here a Minikube cluster, and Minikube is a lightweight single node Kubernetes cluster that can be installed in a simple VM. In the Minikube cluster we have a pod that is running a container, and the container exposes a web service which is running a vulnerable web application that the attacker will exploit to gain initial foothold. Okay, let's get straight to the demo and hopefully it will not break. Let me just switch screen here. Here we have the attacker view and they are trying to attack a website. Let's say the Ossert website. Not the real one, of course. I'm not saying that the Ossert website is vulnerable. Well, I can't say for sure because I have not tested it, but that's the assumption. Maybe some foreign attackers tried to break in and hopefully they are not successful. This is just a local copy of a clone of the Ossert website that I created for the purpose of this demo, and perhaps to reuse it in future social engineering, but with a more subtle and elegant URL than this. Anyways, jokes aside, I added a vulnerable PHP code to that local copy of the website, and now the attacker is going to exploit it to gain remote code execution. As you see here, the attacker runs arbitrary PHP code on the website and gets a shell. They get a shell in the Kubernetes container, but they don't know that yet. All the attacker knows is that they got a shell on some web server. So they start doing some enumeration to get understanding on that web server. They look at the host name, notice that the host name is Minikube, which suggests Minikube cluster. The attacker drops in a shell for further enumeration. They look at the host's IP addresses and sees some local net addresses, which also aligns on what we see or what we have in Minikube. The attacker looks at what services are running on the local addresses. They see a bunch of them. Some things running on port 8443, which could be listening, as we will see in a moment. The attacker looks at the mount points and finds a Kubernetes volume, which will contain the service account token that is used by the pod to interact with the Kubernetes API server. If we look at this file here, let's have a look at this volume first. We see there is a token and a certificate and namespace file. This token holds a JSON web token, JWT, right here. The attacker takes a look at the locally running services like that one on port 8443 we've seen before, issues an HTTP request with curl, and they get a JSON response that looks like from Kubernetes API server, and it says we don't have access because we are anonymous. The attacker can try to authenticate using that JWT token they just found. So the attacker uploads the kubecontrol utility. The attacker has now identified, which we will discuss now, the attacker has now identified that they are running in some container and discovered the Kubernetes API server location on the port 8443. They also found a JWT token for the service account that runs the container. Armed with this information, the attacker can start attempting to query the Kubernetes API server for further enumeration of the cluster. And for the attacker's convenience, they upload the kubecontrol utility, which is a standard Kubernetes tool that can query or perform various administrative functions. There we go, it's uploaded now. The attacker drops back in a shell and runs the kubecontrol utility. So now the attacker can pass that JWT token to kubecontrol and the URL of the API server to perform some basic enumeration on the cluster. For example, the attacker tries to get the running pods on the cluster. It doesn't work. The API server says you don't have permission, and we can see that our service account is called SA demo. So the attacker tries something else, for example enumerate cluster information. Instead of get pods, we see cluster info here. Also no access, it doesn't work as well. So our service account is not fully privileged. It does not have permission to do everything, but there was one dangerous permission granted to that account, which is the ability to get secrets. As we see here, the attacker tries to get secrets, and secrets is like a vault in Kubernetes cluster that stores secrets, which can be username, password, credentials, keys, or any other sensitive information. The attacker discovers that there's a secret called kubeadmin, and they try to dump the secret details by outputting it in YAML format. And we see here we get a username and a password in base 64 encoding. Actually, that's not the one I wanted to show you. We wanted to dump the kubeadmin secret. So we get here a username and password in base 64 encoding. The attacker decodes back the username and the password. The attacker gets a username called Docker user and a fairly good password with upper lower cases, alphabets, and some numbers as well. The attacker can then attempt to log in with these credentials or spray the password elsewhere. So they try to log in, for example, through the exposed SSH interface. In a new shell, the attacker tries to SSH using that Docker user and the password they just decoded. And they successfully log into the Minikube node. The attacker is now in the cluster node itself that is running the pod, not the container from this shell. So they can try to again enumerate all the information that they couldn't do before. We see here that we have kube control utility because this is the node, it's part of the container and it's installed as part of the Kubernetes installation. The attacker tries to list the running pods. They see there's a pod called Osser demo pod. Let's try to list pods in all namespaces. See a bunch of them. Enumerate cluster information, for example. And we see here Kubernetes services running on the local interface. The attacker looks at the deployments, discovers a Kubernetes dashboard deployment, and the Kubernetes dashboard is a web GUI to interact with the cluster instead of running all these kube control commands in the command line. The attacker takes a look at what services are running here. They see something Kubernetes process on port 8001, which is probably the Kubernetes dashboard. The attacker gets something else from the secrets, gets the JWT token used to log into the Kubernetes dashboard, and notice that we are now enumerating secrets in a different deployment, the Kubernetes dashboard, not the Osser demo. So this was not this would have not worked in the previous shell that we were just in. So the Kubernetes dashboard is running on the local host, which is not remotely accessible to the attacker. What the attacker can do is they can set up an SSH tunnel using the same credentials that they discovered, the SSH credentials. The attacker will forward the traffic from their machine to the local host of the remote machine. We again use the same credentials here to set up the tunnel. Now the attacker can try to access their own local 8001 port, and it gets forwarded through the tunnel to the remote machine, to the localhost interface of the remote machine, and we see indeed that we can access the Kubernetes API. The attacker tries to access the full URL of the Kubernetes dashboard, and they are presented to login. We can now log in with that JWT token that we've just extracted. And the attacker gets in to the Kubernetes dashboard. They can see all the cluster information that we've previously seen. And yeah, that's it. Let's get back to the slides. So what was wrong with this setup? We had a vulnerable web application. We had some misconfiguration in Kubernetes where we assigned the dangerous permission to the service account that runs the pod. There is also an increased attack surface with the SSH interface being exposed. These are the commands that I used to create this vulnerable setup. The first one here we see creates a role that has the ability to read the secrets, and the second one creates a role binding which effectively applies that role to a certain account, which is the SA demo service account. And here is the YAML configuration of the pod. We can see that it runs under the service account SA demo, which has that role. Other permissions to watch for could be the ability to create pods. If the attacker can create pods in your cluster, they may provision crypto mining pods and waste your resources. Wildcard can give permissions to all verbs and resources. So for example, you can create a role that has the ability to list everything. The verbs can be things like get or create or delete, and resources can be pods, deployments, secrets. So hardening should be an essential part of your build standard. There are CIS benchmarks for Kubernetes, and there are tools that can help you check and apply these benchmarks, as we will see shortly. Some brief points to note about the pod isolation. This will make it harder for the attacker to break out of the container to the host node. If you set privilege to false, a privileged pod has access to all devices on the host, and similar to any process running on that host rather than being in a restricted container. Allowing host network will share the host network with the pod, giving it access to the loopback interface and any services listening on the local host. Host path lets you mount a path on the host inside the pod. So again, this could be something where the attacker can escape out of the container and access resources on the node itself. Allow privilege escalation will prevent changing the effective user ID. This will break any SUID binaries. So if you have a container that needs to run SUID binaries, be careful with that. Read-only file system will mount the container file system as read-only, which will prevent the attacker from uploading tools as we saw in the demo. Run as can let you run the container as a non-root user. Some additional hardenings to further lock down the container and make it more difficult to escape out could be configure SE labels, SE Linux labels, or AppArmor profiles for your containers. You can also filter or restrict the system calls a container can make using seccomp, and you can refer to this resource for additional information. Okay, let's have another demo to see those tools in action. Okay, the first tool I'd like to show you is Kubernetes RBAC Audit, which can help you identify such dangerous permissions that are provisioned in your cluster. And it works by simply exporting the current roles and permissions in JSON format, and then running a Python script against those JSON files, which will perform its analysis and flag out any permissions. As you see here, it says that there's a role called secret reader that has the permission to list secrets, and this role is bound to the SA demo service account, as we've seen in the demo in the lab. So this can help you identifying such permissions simply and acting accordingly. The next thing I would like to show you is kubesec, which is a security analysis for Kubernetes resources. It can be installed in multiple ways. I have it here as a plugin to kubecontrol. So kubecontrol has a plugin management called Krew, K-R-E-W, and I have it installed as a plugin to kubecontrol where I can run it against a certain pod. For example, let's try to scan the Aussert demo pod. running it like that, kube6 scan, and then give it the pod. It scans the pod and gives us a finding about sharing the host network. It says processes in the pod can communicate with the host's loopback adapter. Very straightforward. The other tool is kubebench, and you can simply run this to perform the CIS benchmarks. Kubebench runs the CIS benchmarks and reports back the findings. As we said before, these hardenings should be standard part of your build procedure, and hopefully that was very straightforward and simple. Let's get back to the slides. A couple of other relevant talks by our COO Mario Goldschmidt. I'll hand it over to Willem here to tell you more about this.